Okay, welcome to Level 1 Science Online with Henny van Vieren.
Welcome back, Year 11s. We're going on with our journey to infinity and beyond and learning about forces. Now, basically, today we're going to have to talk about mass and weight again. Remember last time we talked about it? We said mass is how massive you are. And I know I'm repeating it a lot, but they are going to ask you this. Explain the difference between mass and weight. So, mass is how massive you are, in other words, the number of particles you are made up of. It stays the same irrespective of location, whereas weight is the downward force due to gravity that a planet exerts upon something. Okay? And this changes due to position. If you are on the moon, your weight force will be less. If you are on Mars, it's smaller than the Earth. Your weight force will be less. If you are on Jupiter, it is way more massive than the Earth. You will be way more weighty. Okay, a lot more weight force is going to be pulling on you. All right, now on Earth, we basically calculated that the downward acceleration, the downward acceleration that the gravity of Earth is exerting upon all of us is 10 meters per second squared. So if you weren't sitting, if you were free falling, I'm free falling. Anyways, if you were free falling, then you would be accelerating. You'll be going faster, 10 meters a second, for every second that you are falling. So for the first second, you will go, at the end of the first second, you will be going 10 meters a second. Now for the second second, you're going to go another 10 meters a second faster. So that means at the end of the second second, you're going to be going 20 meters a second. Do you understand? So that is what this refers to. So we're basically going to take your weight force is your mass, how massive you are, multiplied by gravity. And that gravity is an acceleration. Okay? It is still acceleration. Gravity is just the acceleration of the pull of the earth upon us. So weight force is F equals m times A, or F equals m times g. Now remember this, you only use this when you're working in the up and down direction. Okay? The up and down direction. If you're pushing something along, that's a different force. But the up and down direction is the pull of gravity. Okay, so, and that G is always 10. That's a constant, it never changes. And they actually give it to you in the exam. Okay, so they would say G equals 10 meters per second. Okay, let's go to the next one. So then, weight can be measured with a spring balance or another balance. So you take your mass and then the weight force pulling it down to earth is going to change the shape of that spring. It's going to extend that spring, and that is how so we call that a force meter. And when you look at a balance, it if you put a mass on there, it pushes down. Now the calculations when in your bathroom scale, um, you're actually measuring the mass of yourself, but they've already calculated that and multiplied it and got it into your weight force. Okay, so your mass changes, therefore your weight force changes, therefore you either gain weight or you lose weight. Alrighty, so weight force. Now the scale will be read in newtons. Weight can be measured with a spring balance. Mass can vertically hang and the weight can now be read on the force meter. The scale will be in newtons because weight force is newtons. Mass is kilograms. Please, I know it's confusing because we talk wrong in general population. Okay, we say our weight is 2 kilograms. That is not true. Okay, your weight is always a force. Weight, force. Your mass is your massiveness. So, scales, that mass is sitting there, it's being pulled down by the earth, there's a spring in there that gets changed and it moves the scale so that you can see how massive you are. But it's already converted, that's why they call it a scale, because it's the scale has been calculated. Okay, so these are all our SI units, our standard international units. So force, weight force is in newtons, and spring balance mass is in kilogram, how massive you are, and we use scales for that. Motion is in kilometers per hour and so forth. Okay. Now the mass of the earth creates an acceleration of 10 meters a second. We already said that. It does not matter what the size of that thing is. They all fall with the same acceleration. But because of our shape, we have different air resistances. And some objects will experience a different air resistance or opposing force. So to calculate our weight, which is a force on an object, the gravitational field, we must multiply our mass by gravity. Okay, so your weight force is going to be your mass times the Earth's acceleration. Just remember, we are not upside down. Mass goes towards the middle, the center of the Earth. So if you're standing, I don't know where he's standing, it looks like the North Pole. His down is still down. This guy's down is still down. That's why they say we are standing upside down when you're in New Zealand or in Australia, but that's really not true. Our down remains down. It's just, yeah. So just keep that in mind. Okay, I just want to pause here and ask you to watch the video link that I've put in the description on the OLE, which talks about and shows you when we talk about the differences in when they talk about here, regardless of your size or your massiveness, they all fall at the same acceleration. There's a great video where no, I can't remember his name, but anyways, it's quite a famous physicist where he goes into a massive, when I say massive now, I mean a huge vacuum chamber, and they pump out all the air, and then they drop a bowling ball and a feather, and you can see what happened. It's really cool. Please watch it, please, and then you'll see that it's just because of the air resistance. If there's no air, things will fall at the same. Um, they will be accelerated at the same velocity. Okay, so just pause over here. I really hope you guys enjoyed that because that's one of my favorite videos. Brian Cox is an amazing physicist. He actually worked at CERN, which is the Large Hadron Collider. He's really a very clever guy. Anyway, so here's an example of NCEA Mass and Weight, the warehouse. A box in the warehouse has a mass of 2,500 kilograms. Assuming the gravitational acceleration g is 10 meters a second, explain the difference between weight and mass. Remember I told you? So explain the difference between weight and mass. Weight is the force that gravity exerts upon you due to the size of the gravity on a specific planet, and weight force changes depending on your position, whether you are on Earth or on a different planet. Mass, on the other hand, is how massive you are. In other words, the number of molecules you consist of. This remains the same whether you are on Pluto or whether you are on the moon or whether you are on the Earth. Mass is constant, weight is a force exerted by the planet. Okay, told you it will come up. Now, question B. Calculate the weight force of the box. So, let's try this. So weight force equals m times a, but in this case it's g. Alrighty, and so we have mass and we have G. So 2,500 times 10, easy peasy, 25,000. And what is our, no, I can't write with a mouse, 25,000 Newton. Okay, so there you go. Let's see the model answer. Yep, they got the same as we did. Alrighty, mass and weight. Question 2. The kereru, remember all those questions about the kereru, the wood pigeon? Now it's one of the largest wood pigeons. No, it's one of the largest pigeons in the world. Explain the difference between mass and weight. Here it comes again. Explain the difference between mass and weight. So that's the first part of our question. You want me to say it again? Mass is how massive you are, the number of molecules you consist of, and it is a constant. It does not change. It does not matter where you are. Mass does not change. Weight is the gravitational force acceleration that a planet exerts upon everything upon that planet. It changes due to position because the massiveness of the planet changes. Therefore, the weight force will change. Calculate the weight of the Kereru that has a mass of 630 grams. You guys see what they're doing here with us? They're trying to catch us out. What did we use in this one? We used kilograms. And in this case, they gave us grams. So the first thing we need to do, because mass is always in kilograms, okay, we need to change this 630 grams into kilograms. Alright, so weight is the downward force due to gravity that an object experiences due to its mass, while mass is a measure of the amount of matter that an object has. Mass does not change, whereas weight changes due to your position on different planets. Define and compare mass and weight. Mass does not change when location changes, while weight does. I'm sorry it repeats so much, but you have to be able to give this definition, okay? This being given as any person on Earth or on the Moon. Mass, explain mass does not change, but weight can. And then lastly, show the working. Mass is measured in kilograms, while weight force is a force, and all forces are measured in Newton. And there you can see, I change it to 0.6 first, multiplied by 10 gives us 6.3 Newton. Okay, so there's the actual question. This came out of 2015, and you could get merit for this just because you had to change 630 grams to 0.63 kilograms. Merit. Ha! What a bargain. If you didn't do that, you could only get achieved. Okay, so we just read through this, and there we go, 0.63 kilograms multiplied by 10. In 2016, they said a small rocket has a mass of 2.6 kilogram and a weight force of 26 newtons. So they did that calculation for us already. No way. Explain the difference between mass and weight. And this time they give you merit for this. Wow. Okay, so you know what this is about. I'm not going to read it again. You can read it again. 2017, mass and weight in a waka ama. A waka ama is a lightweight outrigger canoe made and used by the Maori. Waka ama is very lightweight. This one is 9.9 kilograms. Holy heck, what is the difference between mass and weight? See, I told you it's going to come up. Alright, use the waka ama as an example and include a calculation for weight. Woohoo! And what do we use for that? F equals MA. And in this this case that A becomes a G. And our mass is 990 and G is 10. So that's going to give us 99 Newton. It's really difficult to write with a mouse. Anyways, please forgive me, I know it looks terrible. Alright, so weight is the downward force due to gravity that an object experiences due to its mass, while mass is a measure of the amount of matter that an object has, or mass is the amount of matter, or weight force due to gravity. Mass does not change when the location changes, while weight does. This can be given as an example of the Wakayama that has a mass of 990 kilograms, but due to gravity, then the weight is weight force m times g equals 9.9 times 10 equals 99 newtons. Okay, so the science of skydiving. Now, this is really important because a lot of us, we've seen skydiving videos, and when the guy opens his parachute, it looked like he's going up, but he's actually not going up, because what you need to remember, even in this picture, there's 3 skydivers. The one skydiver, just like this guy over here, you can see there's a camera on his helmet. So we're looking from the other skydiver that is on this guy in the middle here. He's the student, and we're looking from the other instructor, which is on the other side. And when the person opens their chute, they look like they're going up, but it's actually the camera that keeps on falling. It's not the person that goes up. Now this student loses control and then regains control, so it's kind of it's a really cool video. So let me just show that to you. I'm not allowed to play the music, otherwise they will hit me with a copyright infringement. But anyways, so there you go. They're stabilizing him. They're stabilizing him. Ah, I'm losing control. I'm losing control. Oh my goodness, I'm losing control. And I'm out of control. And luckily, he managed to open his chute even upside down. That is crazy. Now this is from the other camera point. Look at this guy dive after him. He's really trying to save the guy. Oops. No, down. Watch. That is so cool. Anyways, but the guy, see that guy with the camera? We're falling past him. He's not going up. He's just suddenly falling a lot slower. That is very important, that you don't go up when you open a chute. You just fall slower. If we were looking from the Earth, we would see that he's just falling slower. Even though it looks like he's going up, it's because we, with the camera, we are still falling and we haven't opened our chute yet. Okay, keep that in mind. Here's a video that just explains. Okay guys, so I'm going to give you another link to this video, The Science of Skydiving. It's really important that you actually watch this and understand it. There's some good information in there, but there was quite a few, in the past there's been quite a few examples of exam papers with questions about skydivers, and a lot of kids got it wrong. So please go and watch this. I can't show it to you because I think that we'll get pinged for copyright infringement, and I don't want to do that. Okay, so I'll put the link in our task for today. Alright, so please complete, if you haven't done 39, 40 and 41 yet, but all the way from 39 to 45 in your SciPad. Okay, have a great day. Thank you. Bye.